For example 2, using the Nyhaus-Lifton equation on a particular task, I'm going to refer you to page 94 and 95 in your workbook. Page 94 gives you a job description. Go ahead and take a minute to read the job description. Okay, so now that you've read it, essentially you see that an employee is lifting a roll of paper from the cart, and so essentially as she picks it up, she has her back towards us. That's the origin. She steps over to the machine and loads the paper roll into the machine. She's squatting down to load it into the machine. At no point is she twisting her body. She does all the twisting with her feet, and so she's moving her feet to get from the cart to the machine. She has to, at the destination when she's putting into the machine, she has to precisely position the roll, and so we know that she's going to be using significant control. And then one little nuance about this problem is she only does 4 lifts per shift, so 4 lifts in 8 hours. That means we need to use the smallest frequency in our table and the smallest duration. And so even though it's an 8-hour job, she has so much rest in between these 4 lifts that we count it as essentially a low duration task. Okay, so that's going to be something particular for this problem. We go in and we want to fill out the job analysis worksheet. We're going to start with the top, whatever department. I just called it the printing department. The job title is a paper loader. We're going to put your name and as the analyst and today's date as the day we're looking at it. And then job description will be load paper rolls. Okay, from there, and again, I just want you to get used to filling that part out so you don't lose track of information. But from there, step 1 is where I start evaluating for correctness. We input on object weight the weight of the paper roll. We put it in both the average and max. That's 36 pounds. So the paper roll weighs 36 pounds. It's always a 36-pound roll, and so that will be our average as well as our maximum load. Hand location at the origin when she's lifting it up off the cart. They tell you up in the word problem, they can't show you the picture, but they tell you in the word problem that she's reaching 15 inches. And so 15 inches between her ankles and her middle knuckle on her hand, horizontally. The vertical location is the height of the cart. She puts her fingers right at the top of the cart, bottom of the paper roll, and so vertically her hands are 27 inches off the ground. When she puts the paper roll down at the destination, when she loads it into the machine, you see that her horizontally, her distance between her ankles, and you can see they're staggered ankles, so the middle of the 2 ankles out to her middle knuckle is 20 inches. And then vertically, her hands are holding the paper roll underneath the paper roll, so underneath the load, and you can see that that's 10 inches on the drawing. Vertically, the distance the load has traveled is your absolute value of V at the destination, which is 10 inches, minus V at the origin is 27 inches. Absolute value is equal to 17 inches that it's traveled. At the origin, she is twisting with her back, twisting 0 degrees, so she's facing the load, facing the cart. When she puts the load down at the destination, she again is twisting. You can see that in the picture. She's directly facing the load, so she's twisting 0 degrees. Notice that she's twisted with her feet, so the 90 degrees between the cart and the machine is 90 degrees, but she's done all this twisting with her feet, with her ankles, through foot movement, and so she never twists her back, and so there's no asymmetric angle. Lifting frequency. Again, this special case, it's so infrequently done, only 4 times per day over an 8-hour day. So we want to use the lowest frequency. It doesn't hurt your body. Lowest frequency, so less than 0.2. And the duration has so much rest time that it's considered a short duration task. It's basically 1 lift every couple hours. Short duration, and so use the less than 1. And coupling, recall you use the table, identify good, fair, poor. In this case, it's a big round paper roll. She can't get any type of grip on it, and so it's a poor. It's round. She can't bend her fingers around 90 degrees around the edges, and so it's a poor grip. From there, you always do the origin, always evaluate it, because it's always potentially risky. And so starting with 51 pounds, you fill in HM based on the origin H. It's 15 inches. Take 15 to your multiplier tables. You find that your multiplier should be 0.67. Vertical multiplier, knowing it's 27 inches, should show you that your vertical multiplier is 0.98. Distance is 17. Look at the DM table, should be 0.93. AM is 1.0, you're not twisting. FM given, low frequency, low duration, FM is 1.0. And lastly, coupling for poor is 0.90. Once you fill in the boxes, you multiply all those together, 51 times 0.67 and so on. Come up with an RWL at the origin of 28 pounds. The destination you do if there's significant control, and so yes, there is significant control. Again, she's positioning the paper load onto the machine. It takes control, her muscular control, to line it up properly to get it on the machine, into the machine, and so she is using significant control, and so we need to evaluate the destination because it's potentially risky. Going back, now we use destination, vertical and horizontal, and so starting with a horizontal will give you 0.50, vertical 0.85, distance is the same, 0.93, asymmetric will be a 1.0 because there's no twisting at the destination. We can copy the frequency, it's always the same between origin and destination. And then in this case, poor is always 0.90, poor coupling, and so you can fill that in without looking it up again. Multiply those together, come up with an 18.1 pounds. From there, we've finished step 3, putting the object weight in for both locations, putting the relevant RWL at the origin is 28, plug it in your calculator, came up with a 1.3. Destination 36 divided by 18.1 is 1.99, or essentially 2.0 if you round it. And so at this point, we've completed the job analysis worksheet, and so we're left with the interpretation. And so first interpretation is, given these lifting indices, a 1.3 and a 2.0, what is the one lifting index of the job? And so we know that you choose the higher LI. So the lifting index for this task altogether is 2.0. So high stress, high lifting index is bad. You want to know what's the worst about this job. The worst is the 2.0 lifting index. And so that indicates the destination is the problem. Okay. From this point, you go into how do you control it. Controlling is, if you go down that same sequence we discussed in the last lecture, is the lifting index high enough to require a mechanical assist? You're going to say the lifting index is not greater than 3, so it does not require a lifting assist. But of course, you can always use one if you so desire. If you've got some sort of lifting device that would load that paper roll, would lower it down, I can think of a cart that could do it, a sling that could do it. So if you have a way to do that, go ahead. If not, it doesn't have to. It's not at such a level that you need to remove the human from it that it's a high hazard. And so from there you go on. If you decide not to do a mechanical assist, you go back to step 2 and find out, well, one option is if it weighs too much, if the RWL is too low, if it weighs too much, then could reduce the load. And so in this case, you want to choose the lower RWL as being the safe weight. Again, that's safe in quotes, so safe weight. In this case, your lower RWL is 18.1. Notice it's destination, destination, so you're choosing the same location for both the higher lifting index, the lower RWL. You're looking at, can you get that paper roll from 36 pounds that it is right now, so from 36 down to 18.1. Could you do that? Well, you could you could have a smaller paper roll, a skinnier paper roll. It's half the size. You could ask your supplier, can you get me paper rolls that are only 18 pounds, 18.1 pounds instead of 36? And they may or may not be able to accommodate that. If they can, wonderful, your problem solved. If not, if they say, no, I can't get you any smaller than 36, or I can only get you 25, or anything above 18, then you go back, is there another way to control the job? And you do that by looking at your multipliers. And so still, destination is the problem. Your smallest multiplier, looking at numerically, smallest number is 0.5. Second smallest number is 0.85, 0.9, 0.93. Can't do anything about ones. And so starting with number 1, she's reaching into the machine. It's 20 inches. So your problem is HM 20 inches. Can you reduce that? And you look at possibilities of reducing the 20 inches. Is one way is she's squatting down, but squatting places the load in front of her body, in front of her knees. That increases this horizontal distance. And so does she need to squat? You might be able to control it without squatting. You might be able to control it by having her hold the load between her legs instead of in front of her knees. So between her legs would get it closer to her spine, closer to her ankles. And you could possibly look at raising the machine, but I need you to tell me I'm raising the machine so that I can reduce H, so reduce the horizontal. Okay, again, in real life, you may or may not be able to do that. If you can't, you move on to number 2. Number 2 is the vertical location. Her hands are 10 inches vertically off the floor. You need to get them higher so she's not so low. And again, it looks like raising the machine. Could you put the machine on a platform? If you can't do that, then you move on to number 3. It's a round roll. How can you get better coupling? Could you add something with handles, a box with handles, or a sling with handles? Yeah, maybe. If you can't do that, you move on to number 4. Number 4 involves, again, changing the distance, reducing the distance. Again, you could lower the origin or raise the destination. Okay, so that entirely solves. In real life, of course, you're going to have to decide what's practical, what is feasible, what's within your budget, and so you're considering all those constraints. But still, if you are considering those things, still you're working through the process of what do we need to change, what really is wrong with a task. This method will help you sort that out. When we come back to class, we're going to be setting up a lab that lets you look at some simulated tasks to allow you to practice taking some measurements on the job. And so we're going to be looking at a lab that has simulated tasks, plus you're going to do the third example in your workbook, the cafeteria problem. You'll do that as part of your lab. And so at this point, the intent is just to get this methodology, this process, step-by-step process, kind of get that down so you understand that.